and we are starting with that analysis. And we are still doing with the Octopus analysis. This is the last day that we're going to do that. We are going to, I'm going to allow those students who are not there when I was teaching this past portion to do, so to screenshot the questions. Then we can also continue with the conversation in the WhatsApp in case there's a one question that you're not able to answer. So can I allow those students who are not there to screenshot the questions? Then we continue from where we stopped. Or we can get back later.
The screenshot.
Of course, you can even share them in the WhatsApp because I think that's okay. So I said this topic is normally you're going to have about 30. This year there was more than 30 questions, 30 marks, not 30 questions from this particular. And are you able to see my screen? Is my screen clear?
Yeah, it's clear.
Okay, good. So with this topic of periodic table, normally I said we expect about 7 marks from this particular end. And we expect the question normally is tested from a synchronized analysis of the atomic structure and periodic table, the chemical families, the structure and bonding. So when you talk about a question from the periodic table, we are specifically dealing with areas of concern, the atomic structure and periodic table, the chemical families, and the structure and body. So whatever an examiner is bringing, or rather a question from this, we are going to be finding those questions of now select the elements that are in the alkali metals, compare the melting point and boiling point of sodium and potassium, write an electronic arrangement of the particular metal. And that is now we are dealing with the synchronization, the synchronized tests of three particular topics. So it's very much important for you to be able to understand. So going forward, remember that wherever the exam is going to be tested, especially in paper 2, we are going to test all concepts that are related to this. And that is why I've meant this Octopus analysis to be able to synchronize and understand those particular methods. So you can screenshot. This is a question of 8 marks. We have done this. So you screenshot the questions. Have you done the screenshots for that? Mafanya? Another screenshot. We have not done that. Another screenshot. Do it. Good. You share screenshot later. There's no problem with that. I think that is the end of those questions. Now we can go to the answers. So now, tulikuwa tumefika hapo, si ndio? We have done that, the preparation of gases.
Yes.
Yeah, good. So now we go to the, we are saying like now an exam can be tested whereby you are told to prepare state one use of element X. You can be told to draw a well-labeled diagram to show how gases J. The J we are talking about here is oxygen, gases, gases L, this is hydrogen, and gas B, which is fluorine, can be prepared in the laboratory. So you invoke those concepts, and always there'll be a question on the gases. They'll never miss, so it's very much important for you to be able to understand that. So we continue now. Now, draw a well-labeled diagram to show how the chloride of R and chloride of Q can also be prepared by direct synthesis. We also prepared that. We also prepared this one. I think that is where we stop. I think this was the last thing that we were talking about, the strongest oxidizing agent. And that is where, again, where I'm starting from. When you're told to pick the strongest, when you're told to pick the strongest oxidizing agent, what is the examiner looking for? The strongest oxidizing agent, the strongest reducing agent. What are you looking for? Students? When you're told to pick the strongest reducing agent and the strongest oxidizing agent, what is the focus on the examiner? Can somebody try to answer that question again? Because we did that. It's a lot of
when we're looking at the most electronegative or the strongest oxidizing agent,
yeah,
we are looking for the element that's got the highest tendency to gain electrons.
The strongest, the stronger reducing agent, rather the most electropositive, you're looking for the element that has the highest tendency to do what?
That has
the highest tendency to lose or to gain. Stronger reducing agent.
The strongest reducing agent is the one that's got the most electronegative is the one that's got the highest tendency to gain electrons.
To gain electrons. And it is also called the strongest oxidizing agent, isn't it?
Yes.
Or rather, the more reactive non-metal. So what about the strongest reducing agent?
So the strongest reducing element is the one that's got the highest tendency to lose electrons.
Yeah, students, can you get this one right? Huh? So if you are taught to pick the strongest reducing agent, it is the same being taught to pick the most reactive metal. The strongest reducing agent is synonymous to the strongest, to the most reactive metal. That is one, number one, or the most electropositive, or the element with the highest tendency to lose electrons. So that is the strongest reducing agent. And I think you're capturing that point clear, that the strongest reducing agent is always the most reactive metal. It is the metal with the largest atomic radius. So when you're trying to pick the stronger reducing agent, the most electropositive, or the most reactive metal, you are looking at that metal that can easily lose electrons. And how do you know the metal that are the highest tendency to lose electrons? That metal must be having the largest atomic radius and the least number of electrons to be lost. And that automatically tells you to be what? They are making a lot of noise. That, of course, I've muted everybody. So if you want to talk, you unmute yourself to remove those particular allotropes who do not know how to unmute, who don't know how to mute themselves. So we have to, of course, mute them. Now, I have said the stronger reducing agent is also the most electropositive element, and also the metal that is highly reactive, rather the more reactive metal. In such kind of a scenario, you always go to the metal with the largest atomic radius and fewer electrons to be lost. So you go for group 1, the one that is at the top, at the bottom now. So in that kind of a scenario, the strongest reducing agent here is which element? Student.
Yes.
The stronger reducing element is there is what? The stronger reducing agent?
Element K.
K.
Element K, yeah.
K. It has to be, even if there was another element here, you still go to K. Because even if there was M here, K reacts by losing 1 electron, M by losing 2. So the one that easily loses is what?
K.
K.
It is K. So in that kind of a scenario, again, we're also going for the most electronegative, the strongest oxidizing agent, or rather the more reactive metal. Those terms, they mean the same. Of course, you can also add here, kuna kitu nilisahau hapa. For metals, you can also be told that select the element with the lowest ionization energy. It is still the more reactive metal. Naelewana?
Yes.
Yes, very important. So now for non-metals will be the most electronegative, strongest oxidizing agent, most reactive metal. Here you go for which group?
Group 7.
Group 7.
7.
The top or bottom?
The top.
The top. So we are talking about now, this must be the non-metal with the smallest atomic radius now, so that it can grab, it can attract the electron to the cell. You know, if it is very large, you know, whatever causes the attraction, the magnetic attraction, it must be the protons which are within the center. So if the atom is very large and the electron is being removed from very far, it will require, it may not be very easy to remove, but when it's just here, it is very easy for the electron to be pulled and to go back to the what? To be attracted to that particular atom. So we are talking about the strongest oxidizing agent, or rather the more reactive metal, will be an atom with a smaller atomic radius and fewer electrons to gain, and that automatically takes you to group 7, the one that is on the top. And I think that is very, very clear. I think that is very clear, boys.
Yes.
Yeah, I think that is very clear.
Yes.
So that is those are the elements. And of was it? Somebody has not understood.
Yes.
Nani, Uliza, where have you not understood?
Where you've said, does the strongest oxidizing agent have the smallest atomic radius?
Yes, he has some small atomic radius, but it must be in group 7. Don't go for helium. Don't go for something like helium. You know, that one may not work, or maybe hydrogen. It must be a non-metal with a small atomic radius and exclude exclude what? Exclude the noble gases. Normally go to group 7. Normally, the strongest oxidizing agent you go for group 7. The strongest reducing agent for you go for group 1. Naelewana?
Yeah.
Yes, yes. I think that's clear. We can move to the next. Compare the melting point and boiling point of the oxide of T and S. T is what and S is what? Somebody to answer that question again.
T and
T is
S, T is carbon.
S is silicon.
So T will be having which kind of oxide? The oxide of T is what?
Carbon 2 oxide.
Gas.
Silicon oxide.
Okay.
Gases.
Okay, good. So now, what kind of bond exists in carbon dioxide?
Okay, so
What kind of a structure and bond?
the oxide of T, which is carbon 4 oxide, is a simple molecular, and it will have a low melting point and boiling point because it has to weak van der Waals process. And also S, when we come to S, the oxide of S, which is silicon 4 oxide, is a giant covalent with a strong covalent bond, and it will have a higher melting point and boiling point.
The oxide of S has what kind of a structure?
A giant covalent.
Yeah, covalent. So student, listen, the way Dot has said, that is the, I can hear that is the voice of Dot, isn't it? Michael Dot.
It's mine.
Yes, good, good. Very good, very well clarified. In that kind of a question, listen, students, one is that you, in such kind of a question, whereby the two elements or the compounds you are comparing have different structures, you must mention the structure and the bond. But the starting point, a question of comparison. When you are told to compare, when you are told to compare, your answer must have, when you're told to compare, your answer must have the following, that it must have the, when you're told to compare, your answer must have a statement of comparison. After getting the statement of comparison, if you're comparing bonds with different structures, then you tell us now this has this kind of a structure with this kind of forces. The other one has this kind of structure with this kind of forces. So in this kind of a question, the examiner expected you to write the following, that among the two, which one has a higher melting point? And you say the oxide of S has a higher melting point than the oxide of T, that's the first marking point. Then you explain further and you say that this is because the oxide of S has a giant atomic structure with a strong covalent bond, while the oxide of T has a simple molecular structure with a weaker van der Waals process. So whatever I'm saying is, the first of all, the statement of comparison. The oxide of S has a higher melting point than the oxide of T, because the oxide of S has a simple molecular structure with weak, the oxide of T has a simple molecular structure whereby the molecules are held together by weak van der Waals forces, while the oxide of S has a giant covalent structure with a very strong covalent bonding. So are you getting what I'm saying? Today, for you to score the marks? Nimesema nini?
Yes.
First of all, you have to give us the statement of comparison that this one is higher than the oxide of T. Reason because the oxide of S has a giant covalent structure with a strong covalent bond, while the other one has a what? A simple molecular structure with a weaker
Weak
van der Waals forces.
van
So
der
you can
Waals
see
forces.
there is a marking point for you comparing the different kinds of structures and mentioning each bond and each structure, you score half. So that question might end up giving you 3 marks. Because now you're just taught to compare. But sometimes you may be just be told directly that explain why the oxide of T has a higher melting point than the oxide of S. Very important. Are you getting that right?
Yes.
Good.
Yes.
Yes.
Can you continue?
Yes.
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 Yeah, let's go.
Yes, yes.
Now, mambo ingine ndio hiyo. Compare now the melting point and the boiling point of the chloride of Q and the chloride of S. And before we go to that, because there's always a lot of confusion, the examiner can also tell you to compare the chloride of T and the chloride of S. Sorry, you cannot be told to compare that. You can only be told to compare the oxide of S and the chloride of S. The oxide of S needed to metako, which I've said, the chloride of the chloride of S is silicon chloride, which has a simple molecular structure. The chloride of the oxide of S, which is silicon oxide, has a giant covalent structure with strong covalent bond. What about the silicon chloride? Silicon oxide has a giant atomic structure with strong covalent bond. What about silicon chloride? What does it have? Silicon chloride?
Simple molecular structure.
Simple molecular structure with weak van der Waals forces.
Structure.
Simple molecular structure, that's correct. I've seen somebody said, I don't know who it is, that why are we saying weak van der Waals forces when we always saw that all van der Waals forces are weak? So the concept is very simple, that we are simply explaining that the van der Waals forces, this one has giant covalent structure, whereby it is held together by strong covalent bond, while the other one is held by a simple molecular structure with weak van der Waals, meaning that the forces holding it are weak as compared to the covalent bond, which are strong. Tunaelewana, Jesse Jackson? Unashika,
Excuse me, sir.
Yes.
Yes,
You
Mr.
understood it,
Yes.
You are just explaining, you are explaining. Ile bond ziko pale ni strong, but zile zinashika pale ni weak. So that's the concept that we're talking about now. Now, without wastage of time, can we compare the melting point and boiling point of the chloride of Q and chloride of S? Somebody?
The chloride of Q has higher melting point and boiling point than the chloride of S.
Tick, good.
This because the chloride of Q has ionic structure which are held together by giant ionic bonding, while the chloride of S has simple molecular structure with weak van der Waals forces.
Can you repeat your answer again? I can see the Mange distance was very good. The chloride of
Q has a higher melting point and boiling point than the chloride of S. This is because chloride of Q has ionic structure which are held together by a giant ionic bonding, while the chloride of S has simple molecular structures held together by weak van der Waals forces.
Very good, Trey, although there's a lot of mix-up of your explanations. It's not, so you know the answer, but the way you are mixing up your explanation and talking about, you're talking about something like, you're talking about what? You're confusing bond and structure. So you don't have a giant ionic bond. There's nothing like that. So the things are correct. The concept, the answer there should be as follows: that the chloride of Q has a higher melting point than chloride of S. Yes, that's the first melting point. Now, the one students, the chloride of Q has a higher melting point and boiling point than the chloride of S. In other words, you can also say the chloride of S has a lower melting point and the chloride of Q. Tick. Let's come now to unpacking and unmasking the explanation. And then you say, this because the chloride of Q has a giant ionic structure. The chloride of Q has a giant ionic structure with very strong ionic bonds, while the chloride of S has a simple molecular structure whereby the molecules are held together by weak van der Waals. Don't talk about giant ionic bonds. You know, we don't have that. The structure and your giant ionic structure, the bond is ionic bond. Structure ingine ni molecular or a simple molecular structure with a weak van der Waals.
Does silicon have a simple molecular structure?
Yes, silicon chloride.
Okay.
Naelewa, eh?
Yes.
Yes. So just to remove the spirit of confusion in this kind of a scenario, let me first of all give you the answer before I get. So the chloride of Q has a higher melting point than the chloride of S. That's the starting point. Because the chloride of Q has a giant ionic structure with a strong ionic bond that need a lot of energy to break. While the chloride of S has a simple molecular structure in which the molecules are held together by weak van der Waals forces. Can you screenshot the answer? Then I can try to answer that question further. That student has asked, does silicon have a simple molecular structure? This is not really silicon, but you're talking about silicon chloride. Have you taken the screenshot? Are you getting the concept right?
Excuse me, sir.
Yes.
Before you explain this point, can you go back to the other question that you can screenshot the answer?
You can get there?
The question, yeah, so that you can screenshot the answer, the question, the answer, the question that you're doing.
No problem. This one.
That one. Hiyo. Yes, sir.
Hapo ndio tuko ama?
The answer.
Answer iko. Nimeshapeana. Ama answer haijakuja?
The other question. The one that they're speaking about.
Hiyo.
The oxides of T and S. Okay. To make screenshot bus.
Have you go to the next?
Yeah, we can go to the next one.
You can come and sit here. Patuka. There's more work. Unaenda class. Okay, good. Very good. Now, tuko sawa? Eh? Kwa hiyo mtu weni mangineto hapa aje kupiga kelele hapo. Now, we continue, but just before we continue, I just want to explain some issues. Ividio mtihani itatestiwa. The questions on how bonding it test, questions of bonding. How questions of bonding is tested. So exam setup, the comparison, so that you understand. And before I go to that comparison, I want to clarify something here. The clarification that I want to clarify here is as follows. That the following element, the following substances have a giant covalent bond, rather giant atomic. So giant atomic, we have the following. One, nani anaweza kumbuka giant covalent structures? One.
Silicon.
Silicon 4 oxide. Diamond.
Silicon 4 oxide. Then we have
Graphite.
graphite and diamond. Listen and listen very carefully. So the only compound that have a giant covalent structure are 4. Silicon 4 oxide, diamond and graphite. Hiyo ndio syllabus. Achana na hizo vitu zingine. Kuna vitu zingine lakini sasa hiyo hufai kujua. You should only confine to what is the syllabus. Now, now when we talk about non-metals and their compounds have a simple molecular structure, except those 4. Non-metals and their compounds have a simple molecular structure, except diamond, graphite, silicon, and silicon 4 oxide, which have the giant atomic structure. So whatever you're going to be comparing any non-metal or any compound of non-metal, ujue iko na simple molecular structure, except what? Except graphite, diamond, silicon, and silicon 4 oxide. Does that make your learning very easy?
Yes.
Yeah, see what I'm saying? Nasema hivi. As long as this element ni non-metal, ama ni compound ya non-metal, na umeambiwa to compare the bond, ujue that is simple molecular structure. If it is not silicon, na say silicon 4 oxide, na say diamond, na say graphite, there is something that I have had using my superior powers, which means that some of you are getting confused. So to carry out exorcism of those confusion, now this is the most common mistake that many students confuse, and that is now when you are given silicon 4 oxide and silicon 4 chloride. Silicon oxide is giant atomic structure, but silicon chloride is simple molecular structure. Don't confuse the two. Are you getting on the right?
Yes.
So kumbuke silicon oxide ni giant atomic, but silicon chloride ni nini? Simple molecular. And that is why using my powers and superior powers as an experienced examiner, that's why I've given you the previous. We are comparing the oxide of what? The oxide of silicon and the oxide of carbon. But now we are comparing the chloride of silicon and the chloride of magnesium, because many of the students will also confuse the two. And I think now it is very, very clear. Sasa mtihani itatestiwa aje. Kiza vile mtihani itatestiwa ndio ujue. Comparing, the questions on comparison will be set as follows. I hope you have a pen and you have a notebook. So can you write? The questions on comparison of bonding will be set by the examiner as follows.
Yeah.
1.
Yeah. Repeat.
I've said how questions on comparison of bonding are set. Questions on bonding. Questions of comparison of bonds will be set as follows. The questions of comparison will be set as follows. Listen, 1. Compare metallic bond, giant metallic bond versus giant metallic. What are you talking about now? Giant metallic structure versus giant metallic. So I'm saying, unaweza pewa mtihani whereby I've said Listen, I'm saying you can be taught to compare a giant metallic structure with giant metallic structure. You can be taught to compare that. So this, like for example, you can be taught to compare N and H. Simuliona swali tulikwambia kama hiyo. Compare the melting point of N and H. So I want to give you the tricks. Ukitumia kile octopus technique, you'll be able to understand how to summarize that. So this is the trick. Kama una compare metal and a metal and you're comparing their melting point, utaangalia nini? There are two things that you're going to consider to answer that question. Right, Kizana, eh?
Yes.
So we are saying now we are comparing giant metallic with giant metallic. So we are going to consider two things. One, the atomic radius. Kama sayo kupewa H and N. Which one has the higher melting point? H and N. We did that.
N.
N. Because there's a smaller atomic radius. So
Radius.
get the atomic radius for the same group. So if those elements are in the same group, you go for the atomic radius. The smaller the atom, the smaller the atom, rather the atomic radius, the stronger the metallic bond. Umeelewa hiyo point?
Yes.
So usianze kucram vitu hapa, elewa chemistry. Understand chemistry. In guess, nimesema, if you're comparing two metals and you're comparing the melting point or the boiling point, first of all, when you see any question that is telling you to compare melting point or boiling point, you must invoke the concept of structure and bonding. So in that kind of a scenario, nimesema, come on, compare metal and a metal. You use, first of all, look at the atomic radius. If they are in the same group, the larger the atom, the weaker the metallic bond. The larger the atom, the lower the melting or the boiling point.
Yes.
Have you understood that?
Yes.
So nimesema come in the same group, go for the atomic radius. But if they are in the same period, you don't go for the atomic radius. You go for what?
The number of electrons.
Number of delocalized electrons. The more the delocalized electrons, the stronger the metallic bond. Umeelewa? Umeshika? Oh, I repeat again. Eh?
Yes.
These elements are in the same period, like comparison between group 3, like comparing sodium, magnesium, and aluminum. You go for the number of delocalized electrons, like between sodium, magnesium, and aluminum. Which one has the higher melting point?
Aluminium.
Aluminium, because it has more delocalized electrons and therefore it has a stronger metallic bond. Mmeelewa vile mnaweza jibu swali yote ya metal and a metal, comparing the melting point?
Yes.
Mko sawa?
Yes.
So tumesema angalie kama ni group. The larger the atom, the weaker the metallic. Uangalie kama ziko different periods, like sodium, magnesium, aluminum. The more the delocal, I don't say valence electrons, I'm a number of electrons. It is number of delocalized electrons. That is the chemistry. You have to answer the question as the descendant of a certified working chemical. It's somebody who has swum one time in the ocean of chemistry. So that you use the chemistry language. That this, if you're comparing sodium and magnesium, you tell us magnesium has a higher melting point than sodium, because magnesium has more delocalized electrons and therefore it has a stronger metallic bond. Unaelewana, Unaelewana?
Yes.
Good. Then another comparison, molecular structure for this molecular structure. Molecular structure for this molecular structure. Molecular structure versus molecular structure. Molecular structure versus molecular structure. Unaangalia nini hapo? What are you going to consider there? Like somebody like we have done that. Compare the melting point and boiling point of V and W. Of course, you're going to say it even if you have not done it. So if you're dealing with molecular structure versus molecular structure, you go for what?
Go for the atomic size.
You go for the size of the molecule. That if they're in the same group, unaangalia tu yenye iko chini will have a higher melting point. Because automatically it has the same number of what? It has the same atomicity, and also it has a larger atomic radius. Because if you're comparing non-metals in the same group, automatically like 7 in group 7 or group 8, automatically the atomicity is the same. So ile iko chini ndio itakuwa na higher melting point. So if you look at the size of the molecule, the larger the molecule, the more the van der Waals forces. But yes?
You've said something about atomicity.
Atomicity is when you're dealing now with the, nimeanza kwanza aje tuanze kama, for example, kama group 7. Group 7, all of them are diatomic. Diatomic ukiambiwa kama, who is that? Nani ameuliza hiyo swali?
Sabel.
Alvin Habel.
Can you write the formula of chlorine gas? Inaandikwa aje chlorine gas?
Cl2.
Cl2. Chlorine?
Cl.
F2. Sindio? Zabel. That correct?
Yes.
So, ndio tunasema any molecule of group 7, it has 2 atoms. So hiyo ndio tunaitanga atomicity. We say group 7 are diatomic molecules. Na ujue tunaongea mambo ya simple molecular structure. So we are talking about the forces holding the molecules together. Tunaelewana?
Yes.
So that is the point. So like in group 7, you can simply say unaangalia yenye iko chini kiasi ya larger molecule. But now when you're comparing something like chlorine and argon, or sulfur and chlorine, phosphorus and chlorine, you have to invoke the concept of atomicity. Like sulfur molecule is made up of how many atoms?
That's 8 atoms.
So we say sulfur is what? In terms of
Octatomic.
atomicity, tunasema sulfur is octa-atomic. Octa, 8. Octa-atomic. Phosphorus is what?
Tetratomic.
Tetra-atomic. Chlorine is diatomic.
Atomic.
And argon is mono. So comparing the sulfur, we can just write for all about to.
Oh.
That is the molecule of sulfur, 8 atoms. This is the molecule of phosphorus, 4 atoms. This is the molecule of chlorine. And this is the molecule of argon. This is the molecule of argon. Are we there?
Yes.
Now, so which one is the largest molecule between sulfur, phosphorus, chlorine, and argon?
Sulfur.
Yeah, because hiyo sulfur iko na tu vitu twingine ni kama tu mtu kameshikanishwa na twingine 8. So when you get the molecule, this will be the largest molecule, followed by what?
Phosphorus.
Then what?
Then chlorine and then
Chlorine, then argon.
So which element, which molecule there will have the highest melting point or boiling point?
Sulfur.
Sulfur, followed by
Phosphorus.
Good. So now, in fact, this thing, and today, I think I've learned that this concept is not captured in Kelby. Possibly those people who are writing the Kelby, they did not understand this kind of chemistry and immense of them. But of course, this one is captured in top notch. For those who have used it, of course, it's captured when you're comparing the trade in period A. So here we invoke the concept of atomicity. How many atoms per molecule? The more the atoms per molecule, the larger the atom, and therefore the more the van der Waals forces. So if you are taught to compare the melting point of chlorine and argon, you're going to say chlorine has a higher boiling point than argon because chlorine is diatomic while argon is monatomic. Therefore, chlorine has more van der Waals forces than argon. And I think that concept is very clear. Sawa?
Yes.
Yes, good. Yes. That was number 2, how to compare and what to invoke. Then number 3, comparison. Comparison number 3, we are going to compare the following. Giant atomic stroke, giant atomic stroke, giant ionic stroke, giant metallic, giant covalent, umeandika hiyo eh? Giant atomic stroke, giant covalent stroke, giant metallic, giant atomic, giant ionic, giant covalent, giant ionic stroke, giant metallic passes molecular structure. So we are going to compare those kind of things. Umeandika eh?
Pardon.
You can compare giant atomic passes stroke, giant atomic stroke, giant ionic stroke, giant metallic passes simple molecular. Mashika, eh?
Yes.
Good. Very important. So those are issues of comparison. So now we continue. Compare the melting point of elements M and Y. You said that come direct M and Y. Can someone now compare that?
The element M
Hey. What's up? Somebody amepotea kijibu ama?
element M has a higher melting point than element Y because element M has a giant metallic structure made up of strong metallic bonds, while element Y has a simple molecular structure made up of weak van der Waals forces.
Good. Take. And I think now from that kind of analysis is very important. Who is that?
Besides me, Jesse 2D.
Good, Jesse. That's very magnetic. And I think everybody is getting that. Eh? So ukikompare kama M angalia what kind of a structure. Hii ni giant metallic. Y is simple molecular. Unaanza M has a higher melting point than Y because M has a giant metallic structure with a strong metallic bond. While Y has a simple molecular structure with the weak van der Waals forces. This one should be reading. This one should be Y, not this one should be M, not Y. Sawa, not S. Sawa sawa, eh?
Yes.
This one.
Yes.
see. M. This one should be M. This one is element M. So M has a giant matrix, things like that. I think it's correct. Have you done the screenshot?
Yeah.
And today it seems the class is very high. It could very much. Eno kuko hapa?
Iko hapa.
Ah, good. Nini yangu
Yeah.
imeenda hapi, it has turned black.
Ishughulikie hiyo. And kakitu kadogo tu.
Yes.
I remember my lecturer in the university told me that the Van der Waals is of German origin, and in German they pronounce W as V. So we ought to say Van der Waals. Van der Waals forces.
We are saying the pronunciation.
Yeah, the origin is from Germany, and in Germany they pronounce W as V. So we ought to say Van der Waals.
Van der Waals, okay, good.
Allah. Yeah.
Cesar, you can get something from there. But remember, the most important thing is making sure that you also understand the meaning, the way Enoch is saying. That's very good, Enoch.
Yeah.